there's a very close that the electric field is minus V times D. And so that means if the electric field is this way, if we know that V is minus integral E dot ds. Well, V is equal to integral dV. Well, of course it is. Okay, so that means that we can then say that this equals that. Don't forget the minus sign. So dV equals minus E dot ds. Okay, so that is an interesting statement right there. Remember in physics 1, A dot B, this was chapter 3. That's AX BX plus AY BY plus AZ BZ. So that would mean that if we are talking about E dot ds, well, we just need to know what is ds. So ds is our little differential distance. So that's going to be the differential x in the x direction plus the differential y in the y direction plus the differential z in the z direction. So E dot ds is going to be basically EX dx plus EY dy plus EZ dz. Okay. So dV equals minus E dot ds. So dV is minus EX dx minus EY dy minus EZ dz. Now, if we imagine, however, that V is a function of x, y, and z, so you might say that V is equal to 4.2 volt per meter x minus 1.62 volt per meter squared y squared plus 1.85 volt per meter squared yz. Okay, and so you plug in the x, y, and z to get the voltage, so that gives you the particular voltage. So this is just an example right here. Okay, then if you wanted to find the x part of E that's associated with that, then you would look at it and say, now wait a minute, if I imagine this and take a derivative with respect to x, that's going to give me the x part. In other words, EX will be the dV dx, or the partial v respect to x. There'll be a minus in there because we had a minus before. The y component would be minus the derivative of v with respect to y, and the z component will be minus the derivative with respect to z. Okay, so in Calculus 3, you talk about partial derivatives, and so what you find is that the electric field vector would be minus dV dx in the x direction minus dV dy in the y direction minus the derivative of v with respect to z in the z direction. Now this taking derivative with respect to x in the x direction, derivative with respect to y in the y direction, derivative with respect to z in the z direction, this is something that happens a lot in calculus, and so there's a symbol for that, and that is the upside down delta symbol. And so that means take the derivative of x and put that in the x direction, and take the derivative of y, put that in the y direction, and take the derivative of z and put that in the z direction. So we can write full-blown that this is minus the upside down delta of v. Okay, well, we call that the gradient. Okay, and so the electric field is negative of the gradient of the potential, or the electric voltage. And so this is something to be talking about more in Calculus 3, but it does introduce a concept here that we can utilize right now. And that is that there's a direct relationship here. Now, that's assuming that you have a complicated voltage. If the voltage is simple and linear, so in other words, the voltage is completely linear, that means the electric field is going to be linear in one direction. So in that case, it's simple, and that is the electric field is just dV dx if it only changes with respect to x. Okay, and so that means that dV is going to be E dx, so in other words, take the derivative of both, and so the voltage is going to be E times D, where D is that distance integrating from 0 to D. All right, so this is the simple case, and this is how we're going to start, but then know that there are more complicated cases that are out there.